new Okay, and of course, you can have any number of fields on the right-hand side, any number of fields on the left-hand side. But it's a wave function now, and then to calculate the, sorry, I missed that. In order to calculate the density matrix, what I guess we want to do is write total, phi left, phi right, phi left, phi right prime, sum over phi left. Right, but now, plug this expression in. Notice this is our Hermitian operator. This is actually I pi h, right? This is our Hermitian operator, and then that just turns this expression into phi right, phi left prime, and then e to the minus 2 pi h bar. When do I have prime? I have prime over this one, and prime over this one. Somehow phi left is just over phi left. And so again, e to the minus 2 pi h bar. Is that okay? Okay, so that's what we're calculating is the right hand and the right side. That's the difference. Is that the right side? That's the right side. Start with that. That's the right side. Great, fine. Calculate this partition function, not the base to pi, but I know the end, always set by not just a binding diagram, so path integration in addition to the binding diagram. Okay, so let's take a diagram which is such that, for example, far away from the origin here. What will happen? You can characterize the diagram by the internal structure, but also kind of center of mass of the diagram, define it in manner if you like. What's going to happen? You take that binding diagram and integrate its position, the central position of it, around the angular direction. What are you going to get? Factor of beta. A factor of beta. Right. You get exactly a factor of beta. And so when you divide by beta, the result of a diagram like this will be independent of beta, and it will not contribute to the average. This is true for all diagrams of this type, which somehow don't know, which are not sort of wrapped around the origin where the time of beta states. On the other hand, if you take a diagram which does wrap around here, then its whole internal structure actually knows about time of deficit. For example, the distance around here knows about time of deficit. The internal structure of the diagram knows about it. And diagrams which do, let's use the word, become entangled with the this is the horizon, of course, sticks out. Diagrams which get entangled with the horizon, those do depend on beta, or that is to say, they do not pick up a factor of beta when you create the position now.
Could you maybe explain that what you mean by using these time diagrams to compute path integral? I think you said something about drawing curves in space that correspond to propagators, but
propagators are integrals of errors. Sure. Okay. So when I make a diagram, okay, so a diagram, a dimensional point diagram, that is a path integral over three distinct paths connecting these points. Each one of these properties here will be represented as e minus I, or sometimes properties e minus infinite space. Some kind of integral along the lower line of the
and this will come with the Gaussian energy, and this will come with the partial function y of Gaussian energy.
One which is not entangled with the origin of that. Doesn't know anything about this concept deficit. When you integrate it around here, it'll just the only way that it knows about concept deficit. The total excursion and angle is beta. So pick up backward beta, but nothing else. Right? You can think about it for a while, and you'll get the idea that if you take a diagram which is not wrapped around any way around the origin here, and you integrate not only over, but not integrate finally everything else.
Purely topological things. All that matters is the vertices, the edges, and how they're connected. But we're putting them on a space, and it seems that you're saying the diagram being in a different place in this chart you've drawn makes a different diagram.
Yes, let's say the diagram being in a different place. In fact, even putting two vertices here in the same place, I'll regard this diagram as different than that diagram. Okay. We don't have to do this. This is just a picture of what's going on. Right. So if it's not wrapped around here, it doesn't give anything to the entropy. If it's wrapped around, then it will give something to the entropy. And this should ring a bell. I mean, this should ring a bell walking pairs and so forth on opposite sides of the horizon. It's the same bell that practices a bell there. Notice from here goes to there, two opposite things. And of course, they're created in an entangled manner, just like the creation of a vacuum. But we don't need to think about that. This is just a rule. If it's entangled around, if it's wrapped around in any way, any piece of it, for example, is a piece which is not wrapped around, because the rest of it is wrapped around, that's enough to make sure that its internal structure knows about beta. And therefore, when you divide by beta, you in general will not get constant for these kind of diagrams. Okay, so your problem is to work out the sum of all diagrams which wrap around here, and that sum needs to be differentiated with respect to beta, multiplied by beta squared, and then at the end of the day, set beta equals pi. That will give beta something working for. One other point, let's draw in another axis here. That's the axis sticking out of the blackboard. Every diagram also has to be integrated along the direction of the other direction of the problem. That integration gives you a factor of the total area of the horizon. The bigger this is the horizon real space, angularly rotating out. So, in addition to the angular rotation which you take care of, you also have an integration to do over the that will give us a factor of the area of the horizon, the total extension of the horizon, integrating these type of diagrams over a particular direction. So the answer will be proportional to the area. And of course, it's a small, very tiny diagrams which will be able to write divergence. This is too many.
Wait, sorry, what does the angular deficit look like in 3 dimensions? It's
just the question. Okay. Right, you start. I'm not sure. We're looking down at the top of the cake, and we've cut a small slice of the cake.
Okay, so every plane looks the same.
Okay, so that's a formal construction. One of the formal constructions. But among other things, it shows us why the entropy is proportional to the area. Now, we're going to field theory now. We're not doing gravity. So we shouldn't be too surprised if the answer is not infinite. There's a lot of ultraviolet divergence. But let me imagine now an alternate approach. Let me ignore the ultraviolet divergences. An alternate approach is suppose that we are in a theory of gravity. And what we're doing is we're calculating the effective gravitational action. What are we doing to calculate the effective gravitational interaction, the effective gravitational action, when the gravitational field is also interacting with a bunch of fields? Well, what you do is you take geometry, whatever the geometry is, then you calculate the partition function of the quantum fields in that geometry. That would be a function of geometry, or a function of the geometry, and that function would be gravitational action. When you integrate also over the gravitational field.
So assuming that you guys covered arbitrary light loops?
Let's say that for a moment. We're going to come back to that. We could imagine a special kind of graph which just lives on the horizon. It just lives on the horizon, and it happens to have a beta dependence for the moment. And that could be the thing which gives you the first term before the corrections. But we're going to come back to that. We're going to come back to exactly that in a few minutes, I think. Okay, so let's imagine calculating from the gravitational side. After we have integrated out the gravitational fields, we have the gravitational action, which is just a partition function that we calculated in the current background. The curvature now is just convex. So what we'd like to calculate is the Einstein action in the geometry which has a convex. That would include all of these contributions coming from the matter fields after the matter fields are integrated out.
Sorry, can you explain for a second where this relationship between gravitational action and reaction comes from?
It comes from graphs like this. Yes, the theory, okay? Here's graph one. Come to
Then we integrate out.
Yeah, that's right. But the gravitational action, of course, has many, it's not polynomial in general. So there's many gravitons. So we calculate, for example, graviton scattering with a term coming from some possibly bare term, and then corrections coming from these things. And those corrections at the end of the day have to add up to something which you might call renormalized gravitational action. But the renormalized gravitational action is explained in exactly the same form. It's explained in the Einstein form, at least the long distance medium of it. Okay, 1 over 16 by G. That's the integral of R. And how's the integral of R over the entire space with flat everywhere except for convex? Now, there's only 2 dimensions that are coming into this problem. The convex is a strictly 2-dimensional thing. By 2-dimensional, I mean in the RT plane. The other directions are just passive. And that means we can use what's the theorem? The GD theorem. Yes, we can use the Gauss-Bonnet theorem to relate this to the Detzner angle. I'll give the formula. This is another problem that's straightforward and interesting. It says that the Einstein interaction of this geometry with the convex is just equal to, for instance, just define trans beta. This is convex. Define trans beta is convex. Divided by 8 pi G. You just plug in the convex, it works out. Convex is defined minus beta and divided by 8 pi G. Those are 2 separate cells. So this is back of the get graph. And that comes from the rest of the integration. This is an integration of the R, beta, times the other dimensions. And that is back with the other dimensions. Okay, so Einstein Miller gives us a path integral of the action, Einstein Miller action, which is given by this. And some incorrect logarithm cases. Divided by 8 pi is phase number 4 G. Important. We have beta squared d of 1 over beta by d beta. This is the formula of the entropy. Derivative of free energy. This winds up giving us the 2 pi's are taken care of. The area, there's an area. And that's it. So what's beta squared? D by d 1 over beta and beta equals 2 pi. I guess 1. There's a minus sign. So this thing at beta equals 2 pi is 1. And is that 1 for all beta? No, is that 1 for all beta?
But d times 1 over x is 1 over x squared.
Oh, sorry, yeah. Yes. Well, that's what it means, because it's physical...
Yeah, sure.
Okay, you're right. I guess I didn't realize that. Okay. I'm going to keep higher at all. We'll see some resistance. No question. Yeah,
this makes sense. So the vacuum states are tangled left, right?
Yeah.
So why aren't the higher energy states?
Why aren't the higher energy states tangled?
Yeah. Is it different?
Well, the higher energy states have real particles in it. Those particles may themselves be entangled. example, try to calculate the entanglement of the thermal state. That's a universal formula. Is that universal state? Yeah, it's a universal state. By thermal state, I meant that I didn't mean in thermal sense of linear space. I meant in thermal sense of linear space. I want to spend a minute or two just describing in very qualitative terms what a pattern of entanglement in the vacuum looks like. There is a pattern, geometric pattern for it. And I'm thinking now about free field theories, although I could be thinking about scalar variant theory and conformal theory. The pattern of entanglement looks something like this. But this may not be useful to you in thinking about it. I find it useful to think this way. Here's the two-dimensional space. I'm dealing with two-dimensional space, but there's nothing special about it. And now what I'm going to do is sort of tessellate the space. This is one side, this is the other side. This is not time anymore. This is not equal to time stuff. This is a two-dimensional space. And I'm looking at the vacuum. I've arbitrarily divided it by drawing a line in it. And I'm thinking about the entanglement of the vacuum fluctuations. Now, let me now sort of tessellate the two sides here in a scale invariant way. I'm going to divide it up by tiny little cells, here, tiny little cells, here. I'm just subdividing the space into little bits, little pieces. More. Then when I move up, I make the pieces bigger. Twice as big, let's say, twice as high up. Your picture? I'm not going to try to be careful. Go another step, you get twice as big. They could be little circles, for example. Now, the degree of freedom I'm interested in. If you look at the local fields, local means really local. They're tend to be entangled in something very close by. By a local field, I might mean one which is integrated over a very small volume of space. Things which are integrated over a very small volume of space tend to be entangled with nearby things which are about as far away as they themselves are. It's a consequence of scalar variance. So, but that's not what I'm doing here. I'm imagining integrating a field over each of these boxes, and so consider the average field over each one of these cells. Think of the average field as a degree of freedom integrated over each one of these cells. It's not hard to convince yourself that each type has the same integrity. That's scalar variance. This pattern is scalar variant. Entropy is scalar variant. The entropy of one of these cells is a scalar variant thing. So the entropy of this is about the same as the entropy of this is about the same as the entropy of this. But the entropy now means that we integrate out everything else except what's in this box. And how big is the entropy of each one of these cells? Let's suppose it's a single field. There's nothing to depend on. There's no parameter in here. Everything's scalar variant. So a single field, let's say a single free field. The entropy of each one of these cells, the size of the cell, don't think of the size of the cell, is about the same as its distance from the horizon. So when you write the entropy of each, you mean the entanglement entropy of the rest of the world. The rest of the world. Yeah. Right, so then when I drew this line, it's completely arbitrary. So once I've drawn it, the way that I've tessellated it here is not arbitrary anymore. So you mean the entropy of one of these boxes with respect to this? No, with respect to the rest of the world first. First with respect to the rest of the world. Everything. It's going to be mainly concentrated just with respect to everything else.
You know, the entropy is the same way as the lake, right?
What's that?
The entropy of city A is the same as the one in A-1. Is that what you mean?
Yeah, the entropy is the same as the entropy in this region.
Cell, you mean the cell is the same. Okay.
What's the cell? We trace out that first. No, just take a cell. We trace out everything. In other words, there's only if you know, so just keep on the box here, so I'm just going to say that would be a word of entropy. Saying that one unit of entropy means, roughly speaking, it's a big, or cubic, if you like. But, it's each one of these cells have one unit of entropy. That's interesting. But the question I'm interested in is how are they entangled? Who's entangled with whom? Now, by entangled, I'm thinking about the degree of freedom here, which is the average degree of freedom. Average. It's super easy. You draw this in. I mean, if it's one that there's no sense to size here. I just draw a surface. There's one. Yeah, but it's